I'll work on problem number 1. So this problem says that the Maclaurin series for a function is given by this series, and they've spelled it out for you here with a general term, and converges to f of x for absolute value of x is less than r, where r is the radius of convergence of the Maclaurin series, which is sort of the definition of the radius of convergence anyway. So use the ratio test to find r. So the ratio test is the limit as n goes to infinity of the n plus first term divided by the nth term, the absolute value of all that. So the n plus first term of this would be negative 3, n minus 1 plus 1 is the n, x to the n plus 1 over n plus 1. And then instead of dividing by the nth term, I'm going to multiply by the reciprocal of the nth term, which is n over negative 3 to the n minus 1, x to the n. So if I simplify that limit, I'm going to get negative 3 on top, but the absolute value will make that just 3. I'll keep it as negative 3 for now. I get n, which stays up here. I get an n plus 1, which stays here. And I get an x on top. And that's the limit as n goes to infinity. Now, as n goes to infinity, this is the stuff that contains n, and those are going to act like their highest degree terms. So you get something that goes to 1. So this is the absolute value of 3x. And with the ratio test, the series converges, and the ratio test tells you that if this limit is less than 1. So the absolute value of 3x has to be less than 1, which means that x has to be between negative 1/3 and positive 1/3. Now, normally we have to test for the endpoints to see if they're included or not, but this problem was simply asking for the radius of convergence. So really all we need to say is r is 1/3, because that's the distance from the center to the edge of the interval of convergence. So for part B, write the first 4 non-zero terms in the Maclaurin series for f prime. So they've given you the series for f, and now you're finding the series for f prime, first 4 non-zero terms. So the derivatives would be f prime 1 minus 3x plus 9x squared. And then the next term would be this, the pattern that's continuing here. So essentially, if I took the derivative of this, the m would come down and cancel with this n down here, and my derivative would be negative 3 to the n minus 1 times x to the n minus 1. So this is the first, the second, the third. This is the fourth term. So this is going to be negative 3 to the 4 minus 1, which is negative 27, times x to the n minus 1, which is going to be x cubed. So there's the first 4 non-zero terms for f prime. And it says express f prime as a rational function. Now, anytime you see express a series as a function, especially over the interval of convergence, look at the series that you get and see if it's something that we can actually find the sum of. And in this case, this is a geometric series. If I'm multiplying to get to the next terms, my r that I'd be multiplying by each time would be negative 3x. And since this is a geometric series, we're assuming that the absolute value of x is less than r, so it's in the interval of convergence. So that means basically the sum of this geometric series, of which this is the formula, could be written as a function. You can write it as one thing. The first term in this series is 1, and 1 minus r, so that's 1 minus negative 3x, which is 1 plus 3x, and that sum comes out as a rational function. That's what they were talking about, as the x in the bottom. So for part C, it says write the first 4 non-zero terms in the Maclaurin series for e to the x. So you should know that one. That's the n factorial. Haha, let's try that again. N factorial is on the bottom. It's x to the n over n factorial, where it starts at 0. So if I write out these first few terms, all right. So there are the first 4 terms of the series for e to the x. It says use the Maclaurin series for that to write the 3rd degree Taylor polynomial for g of x equals e of x times f of x. So we've got this e of x here, which I'm going to write in numbers in just a moment. And then we've got the f of x, which is what they gave us in the original problem. And we want the third degree polynomial. The other thing is multiplying those two things together. So I'm going to take these polynomials and multiply these things together, but I'm only going to multiply the things that take me up to a third degree. So if I write the e to the x, and I'm going to use the box method here to multiply out, e to the x would be 1 plus x plus 1/2 x squared plus 1/6 x cubed. Now, I may not need all those terms. I'm going to be multiplying that by f of x, which starts with x and goes -3 halves x squared and goes to 3x cubed. And I don't need to list anything higher because it only asks me to get the third degree Taylor polynomial. And any terms higher than that are going to give me things that are bigger degree than 3. So when I multiply these, I don't even need to do all these multiplications because some of these multiplications are going to give me things, again, that have a higher degree than 3, like this one, and 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 I think, and this one. I think the rest of those, though, are going to give me things that are third degree and smaller. So I'm going to multiply those things out. And then write the combination of like terms together. So basically what we're going to say here is g of x is approximately what we got when we multiplied those things out. So that would be x, and I got x squared minus 3 halves x squared, which is -1/2 x squared. And then I've got 1/2 x cubed minus 3 halves x cubed, which is -1x cubed, plus 3x cubed, which is plus 2x cubed.